The universe is mostly made of stuff we cannot see. Dark matter and dark energy are the invisible forces shaping everything around us, and understanding them could reveal the ultimate fate of the cosmos. You will learn how these mysterious dark components control the birth of galaxies and the final destiny of all reality. Why does the universe fly apart faster and faster? And what is the ghostly matter holding it all together? What does it mean that most of the universe is a complete mystery to us? This grand cosmic web presents a profound puzzle. For centuries, we believed the universe was made of the same stuff we see around us, the planets and stars and swirling galactic dust. But this familiar, luminous matter is the rarest substance in the cosmos. The true rulers of the universe are these dark, unseen components. Think of it like this. You are sailing across a vast, dark ocean at night. You can see a few distant lighthouses, their beams cutting through the blackness. You would naturally assume the ocean is mostly empty space between those points of light. But what if you discovered that the entire sea is actually made of a strange, invisible fluid, and those lighthouses are just tiny buoys bobbing on its immense, hidden currents? That is our universe. The stars and galaxies are the lighthouses. The invisible fluid is dark matter and dark energy. Scientists classify them by what they do. Dark matter is the cosmic glue. It has mass and exerts a powerful gravitational pull, pulling things together, weaving the galaxies into that vast web. Dark energy is the opposite force. It is a mysterious pressure that pushes space itself apart, causing the entire universe to expand at an ever-increasing speed. Together, they make up about 95% of everything that exists. Every atom, every star, every person you have ever known is made from the remaining 5%. This realization did not come from looking at what was there, but from noticing what was missing. The first clues emerged from the frantic dance of stars on the edge of a spiral galaxy. A spiral galaxy should tear itself to shreds. The outer stars, whipped around by the collective gravity of the galactic core, move at such tremendous speeds that the centrifugal force ought to fling them into the void. Yet when astronomer Vera Rubin measured their velocities, she found something astonishing. These distant stars were orbiting just as fast as those near the bright center. According to the laws of gravity, this was impossible. The visible mass of the galaxy, all its stars and glowing gas, was simply not enough to hold onto these stellar speedsters. It was as if you spun a bucket on a rope and the rope was invisible. You could see the bucket whirling, but the only thing keeping it from flying away was a force you could not see. This was the first undeniable evidence for dark matter. The galaxy was embedded within a vast, massive halo of something that did not emit or absorb light. This invisible stuff provided the extra gravitational glue, the unseen hand that kept the entire structure from flying apart. But one observation, no matter how compelling, is not enough to rewrite our understanding of the universe. The case for dark matter had to be solidified by other, completely independent lines of evidence. What else could reveal the presence of something that refuses to be seen? Another powerful clue was found not in the spinning of galaxies, but in the oldest light in the universe. This is the cosmic microwave background, a faint, cold glow that permeates all of space. It is the cooled remnant of the universe's fiery birth, the afterglow of the Big Bang itself. Think of it as the cosmic equivalent of the heat you can still feel from embers long after a great fire has died down. This ancient light is a snapshot of the universe when it was just a newborn, a mere 380,000 years old. For decades, satellites like Planck have been mapping this radiation with incredible precision, creating a baby picture of the cosmos. At first glance, this map looks almost perfectly smooth, a uniform sea of microwave light. But look closer, and you see tiny, tiny variations, spots that are ever so slightly warmer or colder than their surroundings. These minute temperature fluctuations are not random. They are a cosmic blueprint imprinted with the secrets of what the universe is made of. The patterns reveal how matter, both the normal atoms we know and the mysterious dark matter, was distributed in that infant cosmos. The gravity from these early clumps of matter left its mark on the light like footprints in wet sand, and the precise nature of these footprints tells a very specific story. The blueprint shows that there was simply not enough normal matter, with its push and pull of radiation pressure, to create the gravitational wells needed to form the galaxies we see today. Something else had to provide the gravitational anchor, a scaffolding that normal matter could then collapse around. That something was dark matter. Because dark matter does not interact with light, it was free to start clumping together much earlier than normal matter could, creating the gravitational seeds for everything to come. Without this dark scaffolding, the universe would be a vast, dull, and structureless expanse. There would be no grand spiral galaxies, no colossal clusters, no cosmic web. The intricate tapestry of the modern cosmos was woven on a loom of invisible threads. This fossilized light from the dawn of time offers our most compelling, independent evidence that dark matter is not just a fix for spinning galaxies, but a fundamental component of reality, one that dictated the very architecture of the universe from its first moments. The blueprint of the ancient cosmos was clear, but the future it predicted held a shocking twist. For decades, the biggest question in cosmology was a simple one. Would the universe expand forever, or would gravity eventually pull everything back together in a cosmic reversal? Astronomers assumed the answer was a gradual slowdown, a gentle cosmic break applied by the collective gravity of all matter. To test this, they turned to the most powerful stellar explosions in the universe, supernovae. These brilliant beacons, visible across unimaginable distances, act as standard candles, their intrinsic brightness allowing scientists to measure how far away they are, and crucially, how fast the universe was expanding when their light was emitted billions of years ago. The results, announced in the late 1990s, were not just surprising, they were revolutionary. The data from these distant supernovae showed that the universe is not slowing down at all. It is speeding up, the expansion is accelerating. This was like tossing a ball into the air and watching it not only fail to fall back down, but shoot away from you faster and faster into the sky. The discovery was so profound it earned the Nobel Prize in Physics. Something was overpowering gravity's relentless pull, a mysterious repulsive force that was given a name, dark energy. Think of it as an anti-gravity effect woven into the very fabric of space itself. While dark matter pulls galaxies together into a vast cosmic web, dark energy is pushing the empty space between those galaxies apart, stretching the very stage on which the cosmic drama unfolds. This accelerating expansion paints a startling new picture of our cosmic fate. Instead of a gradual slowdown or a dramatic collapse, the universe appears headed for a cold, isolated end. Galaxies will be pushed ever further apart, their light eventually fading from view for any future observers. The cosmic web will be stretched and diluted, leaving islands of stars lost in an ever-growing, ever-darker void. This enigmatic force is now understood to be the dominant component of the universe, accounting for about 68% of all the energy density in the cosmos. But what exactly is it? Is it a property of empty space itself, a constant energy field that grows stronger as the universe expands? Or is it something even more strange, a dynamic field that changes over time? The nature of dark energy remains one of the greatest unsolved mysteries in all of science, a ghostly pressure that holds the ultimate key to the destiny of everything we see. So we are left with a cosmic pie chart that defies all intuition. Picture the entire universe, every bit of energy and matter that exists as 100%. The world we know and see, built from atoms that form stars, planets, and life itself, accounts for a paltry 5% of that total. This is the ordinary matter that has been the sole focus of science for centuries. The remaining 95% is the dark universe. About 27% is dark matter, the invisible gravitational glue that sculpts galaxies and binds the cosmic web. And a staggering 68% is dark energy, the mysterious pressure accelerating the expansion of space. This is the fundamental composition of our reality. The stuff we are made of, the world we have built our civilizations upon, is a mere afterthought in the grand cosmic ledger. This profound imbalance is not just a curiosity, it is a crisis for physics. Our most successful theories, which describe the behavior of atoms and the force of gravity with incredible precision, completely fail to explain what 95% of the universe actually is. The rules that govern our visible world are just a tiny, special case within a much vaster and stranger set of laws we have yet to discover. This forces a complete re-evaluation of our understanding. How do you even begin to study something you cannot see, touch, or directly measure? Scientists are forced to become cosmic detectives, looking for the footprints and shadows these dark components leave on the world we can observe. To hunt dark matter, they build incredibly sensitive experiments deep underground, shielded from cosmic rays, hoping to catch the faintest vibration or flash of light as a hypothetical dark matter particle, billions of which might be passing through you every second, rarely and weakly interacts with a normal atom. Others look to powerful particle colliders, trying to create dark matter in the fiery aftermath of microscopic collisions. And astronomers search the sky for subtle distortions, a phenomenon called gravitational lensing, where the gravity of dark matter bends the light from distant galaxies like a giant, invisible lens, mapping its distribution by watching how it warps the fabric of reality itself. For dark energy, the approach is to measure the expansion history of the universe with even greater precision, charting how the acceleration has changed over billions of years. This involves creating colossal three-dimensional maps of galaxies, measuring their distances and velocities to trace the push and pull of dark energy across cosmic time. Each of these methods is a long shot, an attempt to listen for a whisper in a hurricane. Yet this is the painstaking work of uncovering the true nature of the cosmos, a search for the invisible rules that govern everything. These cosmic detectives are not searching for a suspect in a well-lit room. They are hunting in absolute darkness, trying to hear the faintest footstep. To catch a ghost, you need traps of incredible sensitivity, deep beneath mountains, in abandoned mines, and under kilometers of solid rock. Scientists have built laboratories shielded from the constant barrage of cosmic rays and other interference that would drown out their quarry. Here, in the profound quiet, they wait. Their instruments are ultra-pure crystals or vats of liquefied noble gases, chilled to near absolute zero. The theory is that billions of dark matter particles are streaming through the Earth and through these detectors every second. Almost all of them pass through completely unnoticed, but very, very rarely one might just bump into the nucleus of a normal atom. That tiny collision, a vibration smaller than an atom, or a single flash of light, is what these experiments are built to capture. It is like trying to hear a single snowflake land on a pillow during a thunderstorm. So far, no definitive, repeatable signal has been confirmed, but the search continues, pushing the boundaries of sensitivity with each new generation of detectors. Other hunters take a different approach. If you cannot catch the suspect directly, you look for the evidence they leave behind. This is the principle of indirect detection. When two dark matter particles collide, the theory suggests they might annihilate each other, transforming into a shower of secondary particles we can see, like gamma rays or neutrinos. Powerful space-based telescopes are constantly scanning the sky, focusing on regions where dark matter is thought to be densely concentrated, like the centers of galaxies or dwarf galaxies that are dominated by the invisible stuff. They are looking for an unexplained excess of this high-energy radiation, a ghostly signature of destruction happening in the void. Meanwhile, on the surface, the world's most powerful machine, the Large Hadron Collider, takes a third approach. If we cannot find dark matter in the wild, perhaps we can create it. By smashing protons together at velocities approaching the speed of light, scientists recreate the energetic conditions of the early universe. The goal is to blast normal matter apart with such force that new, exotic particles are forged in the fire, including potential dark matter candidates. The trick is that these particles would also be invisible to the detector, but their presence would be betrayed by a telltale imbalance in the energy and momentum of the collision aftermath, a missing piece of the puzzle flying away undetected. And then there are the astronomers who map the invisible directly by watching how it warps reality. They use gravitational lensing, a prediction of Einstein's theory, where the gravity of a massive object bends the path of light from a more distant source. When they observe a vast cluster of galaxies and see the background galaxies stretched and distorted into faint arcs and smears, they are not just seeing the effect of the visible galaxies. The sheer magnitude of the distortion reveals the true, massive presence of the dark matter halo enveloping the entire cluster. It is like looking at a funhouse mirror and being able to calculate the exact shape of the invisible lens that is creating the distortion. Each of these methods listens for a different kind of whisper from the dark, a direct ping, the echo of an annihilation, the birth cry of a new particle, or the subtle warping of space-time itself. They are all long shots, but together they triangulate on the truth. So what exactly are they listening for? What form could this mysterious substance take? The leading candidate is a hypothetical particle known as a WIMP, which stands for Weakly Interacting Massive Particle. As the name implies, it would have mass and interact with normal matter only through gravity and the weak nuclear force, the same force responsible for radioactive decay. This would explain why it is so pervasive yet so elusive. WIMP are theoretically attractive because their predicted properties and abundance could naturally account for the amount of dark matter we observe in the universe. But WIMP are not the only idea. Another intriguing candidate is the Axion, a particle that is incredibly light, potentially trillions of times lighter than an electron. While individually insignificant, they could flood the universe in such unimaginable numbers that their collective gravity would add up to the dark matter we need. Axions are also hunted with specialized experiments that use powerful magnetic fields to try and convert them into faint microwave photons. There are even more exotic possibilities, like primordial black holes formed in the first chaotic moments after the Big Bang, or particles that exist in a hidden shadow universe parallel to our own. The hunt for dark matter is not just a single experiment, it is a whole new frontier of physics, forcing us to question what matter even is. This hunt for an invisible substance leads us deep into the subatomic world, where the leading suspects have names that sound like science fiction. The primary candidate is known as a WIMP, a weakly interacting massive particle. Imagine a particle that is heavy by atomic standards, perhaps dozens or even hundreds of times the mass of a proton, but one that is fundamentally aloof. It feels gravity, and it experiences the weak nuclear force which governs certain types of radioactive decay, but it is completely blind to the electromagnetic force. This means it does not absorb, reflect, or emit light, and it passes through normal matter almost as if it were not there. This perfectly explains its ghostly nature. Billions of these particles could be streaming through your body every second without a single interaction. The hope for detection rests on that almost never, on the 1 in a trillion chance that one of these WIMP will directly strike the nucleus of an atom in an ultra-sensitive detector, delivering the faintest tap that scientists are desperately trying to hear. Yet another compelling candidate turns this idea on its head: the Axion. If a WIMP is a massive ghost, an Axion is an ultra-light phantom. It is theorized to be trillions of times lighter than an electron, so inconceivably tiny that a single Axion is practically without substance. But what it lacks in individual mass, it makes up for in staggering numbers. The universe could be flooded with a cosmic sea of Axions, a dense, swirling fog of these particles where their collective gravity adds up to the immense pull we attribute to dark matter. They were originally proposed to solve a completely different, deeply technical problem in particle physics, and their potential connection to dark matter was a stunning bonus. The search for Axions is just as ingenious, using powerful magnetic fields to try and convert them into detectable microwave photons. Beyond these two front-runners, the possibilities become even more exotic. There are sterile neutrinos, hypothetical heavier cousins to the known neutrinos that flood the cosmos, which also refuse to interact with normal matter. Or perhaps the answer lies not in new particles at all, but in ancient cosmic fossils, primordial black holes. These would not be the black holes formed from dying stars, but ones forged in the incredible pressures of the universe's first second, acting as dark matter seeds scattered throughout space. This dizzying array of candidates is not a sign of confusion, but a testament to the creativity of scientists grappling with a profound mystery. Each proposed solution is a different path through the dark, a different key that might one day unlock the truth. Identifying which, if any, of these candidates is real would do more than just solve the dark matter puzzle. It would fling open the doors to a new realm of physics, revealing fundamental laws of nature we have not yet dreamed of. But if dark matter is an elusive ghost, its cosmic counterpart, dark energy, is an even more baffling phantom. How do you begin to study a force that seems to be a property of empty space itself? Einstein might have been right for the wrong reason. Long before dark energy was discovered, he introduced a concept into his equations called the cosmological constant, a sort of inherent energy woven into the very fabric of empty space. He later called it his greatest blunder, but today it is the leading candidate for what dark energy could be. Imagine space itself is not truly empty, but is a seething, bubbling quantum foam where virtual particles flicker in and out of existence. This frantic activity could endow every cubic centimeter of vacuum with a tiny, constant energy that pushes space apart. If this is true, then dark energy is a fundamental property of the cosmos, unchanging and eternal. The expansion will continue to accelerate forever, but there is a haunting alternative. What if dark energy is not constant? Scientists call this idea quintessence, a dynamic energy field that permeates space but can change in strength over time. It could be weakening or it could be growing stronger. This turns the cosmic forecast from a predictable chill into a deeply uncertain future. If this quintessence field were to intensify, the acceleration could become uncontrollable. The result would be a cosmic doomsday known as the Big Rip. First, the expansion would tear apart galaxy clusters, then individual galaxies. Stars would be ripped from their orbits. Planets would be shredded. In the final moments, atoms themselves would be torn asunder, and the very fabric of spacetime would be ripped apart. This is the ultimate fate if dark energy evolves into a truly dominant force. How do we choose between a constant vacuum energy and a dynamic phantom field? The answer lies in measuring the history of the universe's expansion with excruciating precision. Astronomers use distant supernovae as mile markers, galaxy clusters as cosmic weighing scales, and the subtle patterns in the cosmic microwave background as a fossilized record of early pressures. By combining all these clues, they can trace how the push of dark energy has changed, if at all, over billions of years. So far, the data suggests dark energy is consistent with a simple cosmological constant. But the measurements are at the very edge of our capabilities. The uncertainty leaves the door open for a universe that is far more volatile than it appears. This is not just a debate about the far future, it strikes at the heart of physics itself. The calculated energy of the quantum vacuum is a staggering 120 orders of magnitude stronger than the observed value of dark energy. This is the worst prediction in the entire history of science. It means our understanding of the quantum world and the large-scale universe are fundamentally, catastrophically incompatible. Unraveling dark energy is therefore more than just solving one mystery. It is the key to a deeper unification of all physics, a theory that can finally describe the invisible forces that dictate the structure, evolution, and ultimate destiny of everything. These invisible halos of dark matter were the universe's first architects. In the primordial darkness just after the Big Bang, the cosmos was not perfectly smooth. Tiny quantum ripples stretched across the universe by its rapid initial expansion created minute variations in density. Dark matter, unaffected by the searing radiation that kept normal matter a churning plasma, was free to respond to gravity's whisper. Wherever there was a slightly denser patch, dark matter began to clump together. Over hundreds of millions of years, these clumps grew into vast, sprawling structures, immense gravitational wells in the fabric of space. This was the birth of the cosmic scaffolding, normal matter, the hydrogen and helium gas that would become everything we see, was trapped in a furious dance with light. It was too hot and energetic to collapse, but once these dark matter halos reached a critical mass, their gravitational pull became an irresistible force. The gas was drawn into these deep wells where it could finally cool, condense, and fragment. Within these dark cocoons, the first stars ignited and the first galaxies were born. Without this invisible framework, the universe would be a formless, dim expanse. The gravity from normal matter alone was far too weak to overcome the expansion and pull gas together efficiently. There would be no grand spirals, no brilliant clusters, just a thin, lonely soup of hydrogen drifting forever apart. We owe our very existence to this dark foundation. The evidence for this process is etched into the sky. Powerful supercomputers run simulations of the universe's evolution, starting with those initial ripples and the known laws of physics. When they include only normal matter, the result is a bland, almost featureless cosmos. But when they add the gravitational influence of dark matter, something remarkable happens. The simulation weaves itself into an intricate cosmic web, a vast network of filaments and nodes that mirrors the real universe with stunning accuracy. These virtual universes show galaxies forming precisely where the dark matter scaffolding is strongest, clustering along invisible threads in a celestial dance choreographed by the unseen. Yet this grand structure is not static. The cosmic web is a battleground between two titans. While dark matter's gravity works tirelessly to pull galaxies together into clusters and superclusters, dark energy exerts an opposing force on the largest scales. It is the cosmic tension between the local pull of dark matter and the global push of dark energy that shapes the universe's large-scale evolution. As dark energy accelerates the expansion of space, it makes it increasingly difficult for new structures to form. The gravitational wells of dark matter halos must now fight against the stretching of space itself to pull in new material. In the far future, dark energy may even begin to tear the cosmic web apart, isolating galaxy clusters in an ever-growing void. So the universe we see today, with its brilliant cities of stars, is a snapshot of this ongoing conflict, a fleeting moment where the forces of construction and expansion have reached a delicate and temporary balance. This cosmic tug-of-war dictates the fate of everything we see. In the universe's youth, dark matter held absolute sway. Its relentless gravitational pull gathered the first clouds of gas, ignited the first stars, and sculpted the majestic galaxies we observe today. For billions of years, the cosmos was a story of construction, of matter steadily coalescing into ever larger and more intricate structures, but the balance of power has shifted. As the universe expanded, the density of matter, both dark and normal, steadily decreased, yet the energy inherent in empty space, if that is what dark energy truly is, remained constant. In an ever-growing cosmos, a constant energy density becomes an ever more dominant force. There came a pivotal moment, roughly 5 billion years ago, when the push of dark energy finally overtook the pull of gravity. The expansion of the universe, once slowing, began to accelerate. This was the moment the cosmos switched from building itself up to slowly tearing itself apart. We now live in the era of dark energy's reign. The consequences are written across the largest maps of the universe ever created. Astronomers chart the positions of millions of galaxies, revealing a cosmic web of filaments and vast, empty voids. These voids are the key to understanding the present struggle. Dark matter's gravity still works to pull galaxies along these filaments closer together, but dark energy is pushing the empty voids to expand faster, stretching the cosmic fabric itself. The growth of new structures has effectively stalled. No new giant clusters of galaxies will form. The universe's construction phase is over. We are left with the architecture that already exists, a grand but finite tapestry that is now being slowly drawn out and diluted. This leads to a profound and isolating question about our distant future. If the acceleration continues, what will become of a universe where dark energy is the sole ruler? Our future hinges on the character of a phantom. If dark energy remains a constant, gentle pressure, the cosmos faces a long, slow fading known as the heat death. Over trillions of years, the acceleration will continue. First, the light from distant galaxies will redden and fade, their receding speeds outpacing the travel of light itself. Our observable universe will shrink to the local group of galaxies bound by gravity, and then even those nearby stars will drift into the abyss. One by one, all stars will exhaust their nuclear fuel and die, leaving behind cold, dead remnants, black dwarfs, neutron stars, and black holes. Even these final embers are not permanent. Over timescales so vast they defy comprehension, black holes themselves will slowly evaporate via Hawking radiation, vanishing in a final, quiet puff of energy. The universe will approach a state of absolute equilibrium, a vast, dark, and unimaginably cold void where the temperature is uniform everywhere and nothing ever happens again. It is the ultimate silence, but this slow fade is not the only possibility. Dark energy could be a shapeshifter, a force that grows stronger over time. This scenario leads to a far more violent and dramatic end, the Big Rip. In this future, the repulsive force of dark energy does not just push galaxies apart. It intensifies until it overcomes every force that holds things together. First, it would shred the cosmic web, tearing galaxy clusters apart. Then, the force would grip individual galaxies. The Milky Way would be torn asunder, stars flung into the expanding darkness. As the end draws near, the destructive force would reach into our solar system, pulling planets from their orbits. In the final, terrifying moments, the force would exceed the strength of Earth's gravity, tearing the planet itself to pieces. It would not stop there. The bonds between atoms would be overcome, and nuclei would be ripped apart, dissolving all matter into a sparse, disconnected gas of fundamental particles. Space-time itself would be shredded. The difference between these two fates, a slow freeze or a violent tear, comes down to a single number, the equation of state parameter for dark energy. Think of it as a cosmic dial that determines its pushiness. If this value is exactly -1, it signifies a constant vacuum energy, leading to the heat death. If it is more negative than that, it means dark energy strengthens as space expands, inevitably leading to the Big Rip. Our current measurements place this value tantalizingly close to -1, but with an uncertainty that leaves the door open for either future. This is the driving question behind the next generation of astronomical observatories. Projects like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to map billions of galaxies and thousands of supernovae with unprecedented precision. They are not just taking a snapshot of the universe, they are creating a cosmic movie, charting the expansion history over the last several billion years to see if the push of dark energy has changed at all. By measuring this cosmic dial with exquisite accuracy, we hope to read the final chapter of the universe before it is written, to learn whether our cosmos is destined for a quiet whisper or a final, catastrophic scream. These new observatories are not merely larger telescopes, they are time machines and cosmic cartographers of the invisible. The James Webb Space Telescope peers into the deepest reaches of space and time, observing the very first galaxies as they coalesce within their dark matter halos. By studying their infant shapes and motions, it traces the gravitational influence of the unseen scaffolding from which they were born. Meanwhile, here on Earth, the Vera Rubin Observatory will embark on a monumental 10-year survey of the entire southern sky, imaging billions of galaxies night after night. It will watch for the subtlest of distortions, a phenomenon called weak gravitational lensing. As light from distant galaxies travels across the cosmos, the gravity of intervening dark matter warps its path, ever so slightly stretching the shapes of those background galaxies. By mapping millions of these tiny, coherent stretches, astronomers can literally draw a three-dimensional map of the invisible dark matter web that permeates the universe. Another crucial measurement comes from the frozen echoes of the early universe, patterns known as baryon acoustic oscillations. These are the fossilized imprints of sound waves that rippled through the hot plasma of the newborn cosmos, creating a preferred scale for how galaxies are spaced. The Euclid spacecraft, along with ground-based surveys, will measure this standard ruler across cosmic time. By seeing how this spacing stretches as the universe expands, scientists can precisely measure the push of dark energy throughout history. These are not isolated efforts, but a synchronized global campaign. Each observatory, each technique, listens for a different harmonic in the cosmic symphony. The statistical power of surveying billions of galaxies provides the clarity to distinguish between competing theories of dark energy. Is it truly constant, or does it fluctuate? The data will tell us, yet this flood of raw observation is only one side of the coin. To make sense of it all, we need new theoretical frameworks, new mathematics to describe the 95% of reality we cannot see. But what if the problem is not what is missing, but the rules themselves? A radical alternative challenges the very need for dark matter, suggesting our understanding of gravity is incomplete. This idea, known as modified Newtonian dynamics or MUND, proposes that gravity behaves differently on the vast, sparse scales of galaxies than it does within our solar system. In this view, there is no invisible halo of dark matter. Instead, a subtle tweak to the laws of physics causes stars on the outskirts of a galaxy to experience a stronger gravitational pull than Newton or Einstein would predict, explaining their high orbital speeds without any unseen mass. It is an elegant solution that works remarkably well for individual galaxies, yet this elegant idea hits a wall when faced with the full breadth of cosmic evidence. The cosmic microwave background that fossilized light from the early universe displays a pattern that MUND alone cannot reproduce. The intricate cosmic web of galaxy clusters and the way they bend light through gravitational lensing reveals far more mass than MUND can account for. The Bullet Cluster, a spectacular collision of two galaxies, provides a particularly stark challenge. In this system, the visible galaxies have passed through each other, but the bulk of the mass, mapped by its lensing effect, has been left behind. This is exactly what you would expect if that mass were made of a dark, collisionless substance that barely interacts, and it is a result that modified gravity struggles to explain. While MUND highlights the audacity of questioning our most fundamental assumptions, the collective weight of data suggests the universe is indeed filled with something invisible. So if the answer is not a modification of gravity, then our search must turn inward to the fundamental building blocks of reality. The other path forward is to extend our most successful theory of the small, the standard model of particle physics. This theory brilliantly describes the zoo of known particles and three of the universe's fundamental forces, but it is utterly silent on dark matter and dark energy. The hunt, therefore, is for new physics for particles and fields that lie beyond this established framework. This is where candidates like WIMP and Axions enter the stage, hypothetical particles that would be governed by new yet undiscovered laws. The goal is to weave these new entities into a larger, more complete tapestry of physical law. The ambition stretches even further into the realm of string theory, which proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating strings. The specific harmonies of these strings could give rise to every particle and force, potentially including the elusive dark matter particle and the dark energy field. Yet for all its mathematical beauty, string theory remains, for now, a spectacular hypothesis without experimental confirmation. We are left with a theoretical landscape of stunning diversity and profound questions. Do we change the laws of gravity that govern the cosmos, or do we populate the cosmos with new forms of matter that obey new rules? The answer will not just solve a cosmic accounting error, it will reveal the very bedrock of physical reality. Are the rules that govern the interactions of quarks and electrons the same rules that dictate the fate of galaxies? Or does nature operate with a deeper, hidden layer of instructions we are only beginning to glimpse? The search for dark matter and dark energy is forcing us to rewrite the laws of physics. For decades, two magnificent theories have described our universe, yet they are fundamentally at war with one another. On one hand, Einstein's general relativity paints a beautiful picture of gravity as the curvature of space-time, perfectly predicting the orbits of planets and the bending of light around galaxies. On the other, quantum mechanics describes the bizarre, probabilistic world of atoms and subatomic particles with breathtaking accuracy. The problem is that these two theories speak different languages and break down completely when asked to describe the same event, like the center of a black hole or the first moment of the Big Bang. This is the chasm that dark energy has thrown us into. The cosmological constant, the leading candidate for dark energy, is a perfect example of this conflict. When physicists calculate the energy that should be bubbling up from the quantum vacuum, the result is a number so astronomically large it should have ripped the universe apart in a fraction of a second. The observed value of dark energy is 1 followed by 120 zeros smaller. This is not just a small error, it is the most spectacular failure of prediction in the history of science. It screams that we are missing a crucial piece of the puzzle, a theory that can unite the cosmos of galaxies with the cosmos of the quantum. This is the quest for quantum gravity. Some of the most promising paths forward come from ideas that sound like pure science fiction. The holographic principle, for instance, suggests that our three-dimensional reality, including all the information within it, might be a projection from a two-dimensional surface at its boundary, like a cosmic security camera encoding everything onto a flat screen. In this view, the dark energy problem might be an illusion stemming from our incorrect perception of dimensions. Even more radical is the multiverse hypothesis. If our universe is just one bubble in an infinite froth of universes, each with its own random set of physical constants, then the tiny value of our dark energy is not a law but a lottery ticket. We simply exist in one of the rare bubbles where the vacuum energy is weak enough to allow galaxies, stars, and life to form. In most other universes, the repulsive force is too strong, and everything is blown apart before it can begin. Meanwhile, the hunt for dark matter is a direct assault on the standard model of particle physics. Finding a WIMP or an Axion would be a monumental discovery, but it would also be a doorway. Such particles are key predictions of theories like supersymmetry, which posits that every known particle has a heavier, invisible superpartner. Discovering this hidden symmetry would not only solve the dark matter riddle, but could also help solve the hierarchy problem, another deep mystery about why gravity is so weak compared to the other forces. The potential rewards for solving these riddles extend far beyond cosmology. The very act of this exploration pushes human ingenuity to its absolute limits. The technology developed to detect a single vibration from a dark matter particle could revolutionize medical imaging or create new forms of sensors. The mathematics invented to describe quantum gravity could one day provide the framework for a new kind of computing. When we ask what practical benefits come from staring into the void, the answer might be that we are not just mapping the darkness, we are forging the tools for our own future. The search for the universe's darkest secrets has illuminated our own world in unexpected ways. That same quest to hear the faint whisper of a dark matter particle has produced detectors of almost impossible sensitivity. These instruments, built to sense a vibration smaller than an atom, are now finding uses in medicine. The technology behind ultra-pure cryogenic crystals and sensitive photon detectors is being adapted for new types of body scanners, capable of spotting the subtlest tumors or tracking minute traces of radioactive tracers in the human body with a clarity that was once unimaginable. In materials science, these tools allow researchers to probe the fundamental properties of new substances, watching how individual atoms arrange themselves, which accelerates the development of stronger alloys and more efficient semiconductors. The challenge of processing the universe has also revolutionized how we handle information here on Earth. Cosmological surveys map billions of galaxies, generating a flood of data so immense that it forced the creation of new computational techniques. The algorithms developed to find faint gravitational lenses in a sea of stars are the same ones that now power advanced machine learning systems, helping computers recognize patterns in everything from medical diagnosis to financial markets. The immense data pipelines built for projects like the Vera Rubin Observatory have become testbeds for big data analytics that benefit industries worldwide. And high above us, the drive to see farther and fainter has pushed space telescope engineering to its absolute limits. The precision optics and advanced mirror systems developed for observing the cosmic dawn have direct descendants in the satellites that monitor our changing climate, track environmental shifts, and form the backbone of global communication networks. This cascade of innovation reveals a profound truth about fundamental research. We aim our telescopes at the void to answer grand questions about existence, but the tools we build along the way so often find a purpose closer to home, spinning off into technologies that reshape our daily lives. This journey into the unknown does more than advance engineering. It captures the human imagination. The stunning images of distant galaxies and the profound mystery of the dark universe serve as a powerful catalyst for education, inspiring a new generation of scientists, engineers, and dreamers to look up and ask what else is possible. The profound questions raised by the dark universe ripple far beyond the physics lab, igniting a cultural and philosophical conversation about our place in the cosmos. This journey into the unknown is not locked away in academic journals. It is brought to life under the domes of planetariums worldwide, where audiences are enveloped in immersive visualizations of the cosmic web. Stunning documentaries translate complex data into narratives of exploration, making the hunt for dark matter as gripping as any adventure story. This public engagement is a two-way street, a vital dialogue where the mystery of the cosmos meets the human need to understand. One of the most powerful tools in this exchange is citizen science. Platforms like Zooniverse invite everyone with an internet connection to become a cosmic explorer. You can sit at your kitchen table and help professional astronomers classify the shapes of distant galaxies from telescope images, your clicks contributing directly to the mapping of dark matter's gravitational influence. This is not a simulation, it is real research, and countless volunteers have made genuine discoveries, spotting rare objects or unusual galactic structures that computer algorithms missed. This collective effort does more than just process data. It builds a global community of curious minds, all connected by the thrill of the hunt. In classrooms, the enigma of dark matter and dark energy is a gateway to science itself. Educational programs use these tangible mysteries to spark interest in STEM fields, showing students that science is not a set of settled facts in a textbook, but a dynamic, living process of questioning and discovery. When a child learns that most of the universe is invisible, it challenges their perception of reality and fuels a desire for critical thinking. The goal is to cultivate not just future astronomers, but a society that values evidence, curiosity, and the humility to acknowledge how much we have yet to learn. By sharing the raw excitement of discovery, scientists foster a deep sense of wonder and a personal connection to the cosmos. This engagement is not a luxury, it is essential. It sustains public support for the ambitious, long-term projects that fundamental science requires, and it nurtures the next generation of innovators who will one day build the detectors and telescopes we cannot yet conceive. This widespread fascination inevitably leads us to ask bigger questions. How do different cultures and philosophical traditions interpret a universe dominated by unseen forces? For some, it echoes ancient concepts of a world spirit or an invisible order underlying visible reality. For others, it presents a profound existential puzzle, suggesting that truth is not always accessible to our senses and that reality is far stranger than it appears. Does a cosmos where we are made of the rarest substance instill a sense of cosmic loneliness or a feeling of special significance? The dark universe, in all its mystery, holds up a mirror to humanity, challenging us to find meaning not just in the light, but in the vast and beautiful darkness that gives it shape. This cosmic perspective shatters the old, comfortable idea that the universe was made for us. We are not the center of this story. We are a brief, brilliant afterthought living on the scraps of a cosmos ruled by darkness. This realization is a profound philosophical tremor, forcing a humility that echoes through the ages. For centuries, humanity placed itself at the center of creation, but now we must confront a universe where the stuff of our being is a mere 5% impurity in a sea of invisible forces. It challenges our very notion of reality, asking if what we perceive with our senses is the true nature of existence, or just a sliver of a far grander, hidden tableau. This has become fertile ground for artists and writers who use the metaphor of the dark universe to explore themes of the unknown, the limits of human perception, and our fragile search for meaning in an indifferent vastness. Their works are not about answers, but about capturing the awe and existential wonder of the question itself. This engagement enriches our entire culture, turning data points into a shared meditation on our place in the grand scheme. And this meditation always circles back to the same burning question. With so much at stake, where is the front line of this search today? The hunt has crystallized around several monumental experiments, each a masterpiece of engineering designed to trap a ghost. Deep in an abandoned gold mine in South Dakota, the LUX Zeppelin experiment sits under a mile of rock, its core a tank of ultra-pure liquid xenon. It waits in profound silence for the telltale flash of light and charge that would mark the first direct collision with a dark matter particle. Meanwhile, at CERN, the Large Hadron Collider continues its relentless campaign, smashing protons together in the hope of creating dark matter in the debris of these microscopic fireballs. In Italy, the Xeno-NNT experiment uses a similar liquid xenon technology, racing to be the first to hear that cosmic whisper. And looking to the heavens, the Fermi Gamma Ray Space Telescope constantly scans the sky, searching for the indirect signature of dark matter annihilations in the hearts of dwarf galaxies. These are not isolated efforts, but a global network of ears pressed against the cosmos, listening for the faintest signal that will finally illuminate the dark. A ghost has never been hunted with such precision. The most sensitive ears listening for dark matter are not in telescopes, but deep underground, in tanks of liquid so pure they defy belief. In a former gold mine in South Dakota, over a mile beneath the surface, the LUX Zeppelin experiment waits in total darkness. Its heart is a towering tank filled with 10 metric tons of liquid xenon, chilled to -100 degrees Celsius. This environment is so shielded from cosmic rays and natural radioactivity that it is one of the quietest places on Earth or under it. The entire setup is designed to wait for a single, perfect event, the moment a dark matter particle, perhaps a WIMP, bumps into the nucleus of a xenon atom. That tiny collision would produce a faint flash of light and a puff of electrical charge, a dual signal that the experiment's sensors are built to capture with exquisite sensitivity. A similar, equally ambitious hunt is underway in Italy beneath the Gran Sasso mountain. The Xeno-NNT experiment also uses a huge vat of liquid xenon, constantly purifying it to remove any trace contaminants that could mimic a dark matter signal. These are not passive observatories, they are active traps, and every day they listen is a day they rule out vast swaths of theoretical territory, telling us where dark matter is not, and forcing the search into ever more refined corners of possibility. Yet liquid xenon is not the only way to listen. In a laboratory at the University of Washington, a completely different kind of hunt is in progress. The Axion Dark Matter Experiment, or ADMX, searches for the ghostly action. Its method is just as ingenious, using a powerful magnet and a resonant cavity, a kind of tuned radio receiver, cooled to near absolute zero. The theory is that in the presence of a strong magnetic field, an action could convert into a very faint microwave photon. ADMX slowly tunes its cavity across millions of frequencies, listening for one specific station in the cosmic static, the faint whisper of an action turning into light. And then there are the observers who watch for the echoes of destruction. At the South Pole, the Ice Cube Neutrino Observatory uses a cubic kilometer of pristine Antarctic ice as its detector. Thousands of sensitive optical sensors are buried deep within the ice, watching for the faint blue flashes of light created when neutrinos, nearly massless particles, interact with the ice. Some of these neutrinos could be the indirect products of dark matter particles annihilating each other in the dense core of the Sun or at the center of our galaxy. By searching for an unexplained excess of these high-energy neutrinos from specific locations, IceCube is looking for the shadow of dark matter's secret interactions. Each of these experiments represents a different bet on the nature of the phantom we are chasing. They are the vanguard of a global effort, each new generation 10 times more sensitive than the last, systematically closing the windows on where dark matter could be hiding. But this relentless, multi-pronged assault only targets one half of the dark universe. What about the force that is pushing everything apart? The search for dark energy requires a completely different kind of instrument, one that can map the history of the cosmos itself. These new surveys are not just telescopes, they are cosmic census takers on an unimaginable scale. The Dark Energy Spectroscopic Instrument, or DAISY, sits atop a mountain in Arizona, its robotic array capable of precisely measuring the light from thousands of galaxies every single night. It is not just taking pretty pictures, it is capturing the fingerprints of these distant island universes. By analyzing the subtle red shift in their light, DAISY can determine not only their distance but their velocity, creating the most detailed three-dimensional map of the universe ever attempted. This map is specifically designed to trace the imprint of baryon acoustic oscillations, those frozen sound waves from the early universe that act as a standard ruler. By measuring how this ruler has stretched over billions of years, scientists can plot the expansion history with exquisite detail, watching for any subtle changes in the push of dark energy across cosmic time. Meanwhile, high above the distorting effects of Earth's atmosphere, the Euclid spacecraft is conducting its own silent survey. Its mission is to chart the geometry of the dark universe by observing the shapes of over 1 billion galaxies. It uses a phenomenon called weak gravitational lensing, where the gravity of intervening dark matter subtly distorts the images of these background galaxies. By mapping these tiny, coherent distortions across a vast swath of the sky, Euclid will essentially draw a picture of the invisible dark matter web in 3 dimensions. This map will reveal how the cosmic scaffolding has grown over time, and how that growth has been suppressed by the relentless push of dark energy. The sheer volume of data from these missions is staggering, but it is the legacy survey of space and time at the Vera Sea. Rubin Observatory that will take this effort into overdrive. Over 10 years, this facility will image the entire southern sky every few nights, creating a cosmic movie of unprecedented scale. It will not only track billions of galaxies for lensing and mapping, but it will also discover millions of supernovae, those crucial standard candles that first revealed the accelerating universe. This constant monitoring allows scientists to see the expansion history unfolding in real time, providing multiple, independent lines of evidence all at once. The true power lies in the combination of these colossal datasets. DAISY provides the precise spectroscopic distances. Euclid delivers the high-resolution, wide-field imagery for lensing. The LSST offers the unparalleled statistical power and time domain coverage. When these streams of data are woven together, they create a multi-messenger portrait of the dark universe, a picture painted in optical light, infrared, and the subtle warping of spacetime itself. This collective effort will test our cosmological models with a precision that was pure fantasy just a generation ago. It will measure the cosmic dial for dark energy with such accuracy that we will know definitively if it is truly constant or if it has been changing, secretly shaping a different fate for the cosmos. What if the data reveals a tension, a crack in our standard model of cosmology? An unexpected result from these surveys could force a revolution, perhaps pointing toward a new theory of gravity, or revealing that dark energy is something far more dynamic and strange than a simple cosmological constant. The universe's greatest secrets are not hidden in the darkness, but in the light from billions of galaxies, and we are finally learning how to read it. The greatest discoveries often begin with a single, stubborn anomaly. Our most cherished models of the cosmos, from the cosmological constant to the nature of dark matter, are not set in stone. They are waiting to be broken by a new piece of data that refuses to fit. Imagine for a moment that the next generation of telescopes reveals a subtle but undeniable pattern. The acceleration of the universe was slightly weaker 8 billion years ago than it is today. This single finding would shatter the idea of a constant dark energy. Instead of a gentle, eternal push, we would be facing a dynamic phantom, a force that evolves and grows stronger, pushing the cosmos toward that ultimate big rip. Or consider dark matter. What if we found evidence that it does occasionally interact with itself through some unknown force, creating faint friction within dark matter halos? This would transform dark matter from a perfectly collisionless ghost into a more complex substance with its own hidden physics, a shadow world with its own rules playing out alongside our own. These are not just thought experiments. Our maps of the cosmic microwave background already contain tiny, unexplained anomalies, cold spots or strange alignments that our standard model struggles to explain. The distribution of galaxies on the largest scales might show a faint, unexpected clumpiness. These could be mere statistical flukes, the cosmic equivalent of seeing faces in the clouds. Or they could be the first whispers of something far grander, hints of extra dimensions, new fundamental fields, or a gravity that behaves differently across the vastness of space. History is a testament to the power of the unexpected. The discovery of the universe's accelerating expansion was itself a colossal surprise that overturned decades of assumption. It was a breakthrough that came from following the data, not from defending the old models. This is why scientists must remain open to being completely wrong. The entire point of the search is to be surprised, to find the flaw in our current understanding that leads us to a deeper truth. No single nation or telescope can shoulder this burden alone. The hunt for these cosmic surprises is a truly global endeavor. The data from the Vera Rubin Observatory in Chile is analyzed by teams in the United States and Europe. The Euclid spacecraft, a European mission, relies on contributions from scientists around the world. This international collaboration is not just about sharing costs, it is about sharing perspectives. A physicist in Japan might look at a dataset and see a pattern that a team in Brazil overlooked. This diversity of thought creates a stronger net to catch the subtle anomalies that could change everything. When the next great surprise emerges from the data, It will be because a worldwide community of curious minds was listening together, ready to hear the cosmos tell us we were wrong and to lead us toward what comes next. These vast questions have erased national borders, transforming science into a truly global village. In laboratories and control rooms around the world, you will hear a chorus of languages, a testament to collaborations that span continents. The hunt for dark matter at CERN involves over 10,000 scientists from more than 100 countries, all contributing to the operation of the Large Hadron Collider. In space, the James Webb Space Telescope is a joint venture of NASA, the European Space Agency, and the Canadian Space Agency. Its stunning images are a product of shared engineering brilliance. On the ground, the future square-kilometer array radio telescope will be built across 2 continents, with its core in the remote deserts of South Africa and its outstretched antennas in Western Australia, managed by a consortium of 16 member countries. These are not merely financial arrangements, they are a profound pooling of human curiosity. Each partner brings a unique piece of the puzzle, a different way of thinking, a specialized technology, or access to a crucial piece of the sky. This cultural and intellectual cross-pollination is where true breakthroughs are often born, when a perspective from one side of the world challenges an assumption from another. The foundation of this global effort is a radical commitment to open science. The torrent of data from telescopes like Gaia or the Vera Rubin Observatory is not hoarded by a single team, but released to the entire world, often within a year of collection. This means a graduate student in India can download the same cosmic dataset as a senior professor in California, both free to search for patterns and ask new questions. Open data policies accelerate discovery, turning every research institution on the planet into a potential front line for a breakthrough. It creates a collective intelligence, a global brain focused on solving the same cosmic riddles. This spirit of shared pursuit demonstrates that the fundamental laws of nature are a universal heritage, and understanding them is a goal that can unite humanity in a common, awe-inspiring project. This radical openness is the engine of modern cosmology. The most powerful discoveries are no longer made by a lone astronomer at a telescope eyepiece, but by a global community with access to a shared digital universe. Projects like the Sloan Digital Sky Survey pioneered this philosophy, releasing the light from millions of galaxies onto the internet for anyone to explore. The result was a creative explosion. An astronomer in Brazil could cross-reference the data with radio wave observations, while a graduate student in Japan developed a new algorithm to classify galaxy shapes. Amateur enthusiasts, citizen scientists scanning the same images from their home computers, have spotted rare celestial objects that automated software missed. This is science as a collaborative, living network where a breakthrough can come from anywhere. By throwing the doors to the cosmos wide open, we effectively multiplied the number of brilliant minds on the case, turning a single team's dataset into a worldwide laboratory. This transparency does more than just accelerate discovery, it fortifies the entire scientific process. When every step from raw data to final analysis is open for scrutiny, it builds a foundation of trust and reproducibility. Other researchers can test the conclusions, verify the methods, and build upon the work with confidence, creating a robust, self-correcting path toward the truth. This collaborative spirit is now the standard for the next generation of observatories, ensuring that the flood of data from the Vera Rubin Observatory and the Euclid spacecraft will be a resource for all of humanity. As we look ahead, the question becomes how new technologies will amplify this collective power. Could artificial intelligence not only manage this data deluge, but find subtle correlations no human mind could perceive? Might quantum computing one day simulate entire universes with different laws of dark energy, allowing us to test our theories in a virtual cosmos before confirming them in our own? The future of exploration lies not just in building bigger telescopes, but in forging smarter, more open connections between every curious mind on the planet. The next generation of detectors will listen for whispers we cannot yet hear. Quantum sensors are emerging from laboratories, devices that harness the bizarre rules of the quantum world to feel the fabric of reality itself. These instruments use entangled particles, pairs that are mysteriously linked across any distance, so that a change to one instantly affects the other. This quantum link creates a system of unbelievable sensitivity. The goal is to use this network to detect the infinitesimal gravitational tug of a single dark matter particle, a vibration so tiny it would be lost in the noise of any conventional detector. It is like trying to measure the weight of a snowflake by watching its effect on the entire atmosphere, a task only possible with quantum tools. While some listen for these subtle pulls, others will listen for the echoes of cosmic collisions on a scale we can barely comprehend. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will launch 3 spacecraft into orbit around the Sun. They will fly in a perfect triangle, millions of kilometers apart, connected by lasers. This colossal instrument will function as a gravitational wave observatory in the vacuum of space, free from the seismic rumble of Earth. It will tune into the low-frequency hum of the universe, listening for the ripples in space-time caused by the mergers of supermassive black holes and the remnants of the universe's earliest moments. These primordial gravitational waves could carry imprints from the inflationary epoch, a fleeting instant after the Big Bang when the universe expanded exponentially. By studying these waves, we might see how the push of dark energy has woven itself into the cosmos since the very beginning. But these torrents of new data would be meaningless without the brains to interpret them. The sheer complexity of the cosmos demands a new kind of partner, artificial intelligence. Advanced computational models, powered by our eye, are now creating hyper-realistic simulations of universal evolution. These are not simple animations, they are virtual universes born from equations, where dark matter and dark energy are given different properties to see which digital cosmos grows to look exactly like our own. The eye sifts through the staggering outputs, learning to identify the subtle fingerprints that different dark matter candidates would leave on the galactic scale. It can then cross-reference these virtual signatures with the real data pouring in from telescopes, performing in minutes an analysis that would take a human team centuries. This synergy of human curiosity and machine intelligence is creating a new lens through which to view the darkness. These 3 pillars, quantum sensing, space-based listening, and artificial cognition, promise to illuminate the 95% of reality that has remained hidden. They are not just incremental improvements, they are fundamental shifts in our ability to perceive. What overarching lessons can we draw from this entire journey into the cosmos's darkest regions? It teaches us a profound humility. We have learned that our senses are limited, that the reality we experience is a narrow slice of a much grander existence. It shows that the universe is not designed for our comfort, but is a place of immense, often invisible forces. Yet this journey also reveals our incredible ingenuity. Faced with a universe of darkness, we did not retreat. We dug deeper underground, we launched eyes into the void, and we taught machines to see patterns in the noise. The search for dark matter and dark energy is more than a scientific puzzle. It is a testament to our relentless drive to understand our place in the vast, beautiful, and mysterious whole. This cosmic tug-of-war is the engine of everything we see. the universe is not a static painting but a living, breathing system, a dynamic dance between two invisible partners. On one hand, dark matter provides the gravitational anchor, the sculptor that pulled gas together to form the first stars and weave the cosmic web. Its relentless pull is the reason you and I exist, the force that built the galaxies we call home. On the other, dark energy is the cosmic tide, an expansive force that stretches the very stage of space, pushing galaxies apart and setting the tempo for the universe's ultimate fate. It is the reason the night sky is dark and isolated, a force that ensures the cosmic construction project has an end date. Their interplay is a delicate balance that has shifted over billions of years. In the fiery youth of the cosmos, dark matter reigned supreme, its gravity efficiently pulling the universe into structure. But as space expanded and matter diluted, the constant pressure of dark energy began to dominate. The universe crossed a threshold and the era of acceleration began. This is not a story of two separate forces, but a single, intertwined narrative of cosmic evolution. The grand spiral of a galaxy and the immense void it floats in are both products of this fundamental relationship. Unlocking their true nature would be more than just solving two big puzzles. It would be the key to a unified theory of physics. The rules that govern the cosmos of galaxies and the rules that govern the quantum world are currently at war. Dark matter and dark energy are the battlefield where this war will be decided. Finding the particle that constitutes dark matter would revolutionize our understanding of the subatomic realm, while deciphering dark energy could finally show us how to stitch gravity into the quantum fabric. The answers to these cosmic questions hold the potential to reveal why the universe has the properties it does, why matter exists at all, and what the fundamental constants of nature truly mean. This grand synthesis is the beautiful culmination of scientific inquiry. It connects the frantic spin of a single star on the edge of a galaxy to the faint afterglow of the Big Bang, and then to the accelerating flight of a supernova billions of years later. Each piece of evidence is a thread, and when woven together, they form a tapestry that tells the story of reality itself. We are living in a golden age of cosmology, standing on the brink of revelations that could reshape our place in the cosmos. The detectors are listening, the telescopes are mapping, and the collective curiosity of our species is focused on the darkness, waiting for the next thread to appear. Our journey through the invisible cosmos reveals a universe far grander than our senses can perceive. We have ventured into the heart of darkness, not of emptiness, but of substance, discovering the ghostly matter that sculpts galaxies and the repulsive energy that dictates their final destiny. These are not just abstract ideas, they are the fundamental architects of reality, the hidden keys to everything from the birth of the first star to the ultimate fate of all existence. This pursuit forces us to confront the limits of our knowledge, humbled by the realization that the world we see is a tiny island in a vast, unseen ocean. Yet this same challenge is what propels us forward, driving the creation of impossible technologies and fostering a global community united by curiosity. The search for dark matter and dark energy does more than expand the boundaries of science. It reignites a fundamental sense of wonder, connecting us to the cosmos and to each other in a shared quest for meaning. This cosmic conversation is far from over, and your perspective is a vital part of it. What did these dark mysteries spark in your imagination? Share your thoughts and questions in the comments below, and join us as we continue to explore the greatest enigmas of space. Remember to subscribe so you do not miss the next journey into the unknown.